Hi everyone, and welcome to this video on evolutionary serverless. What the heck is clean hexagonal and onion architecture? So a little bit about me. My name's Lee Gilmore. A lot of people will know me as the serverless advocate. So I'm an AWS community builder, content producer, and technical writer based in the northeast of England. And you can use that QR code or go to serverlessadvocate.com to find out a little bit more about me. So today we're going to cover why do we need evolutionary architecture, a brief history of time, where do we land in serverless, and that's going to be examples in TypeScript and the CDK, and then a demo and a code walkthrough. So we live in this world where everything is changing and evolving continuously. Everything from the global climate to laws, politics, and even the evolution of the human race. And as we sit here, our phones are pinging us with notifications on the latest news, weather, and changes in the economy. And in the past 5 or so years, we've had big advancements in blockchain, Web3, and now AI. And even the cloud services that we're using daily are changing feature-wise or being superseded by other services. So everything is constantly changing around us. Now, we knew this back in the days of Marcus Aurelius. For anybody that's into Stoicism, this is a great quote about change. Now, unless you're into Stoicism, this is quite a difficult one to actually read. So let's do an AI interpretation of this quote, a 2024 example using AI. And it would be always remember that everything is constantly changing and embrace the idea that the universe thrives on transformation, continuously renewing itself and creating new versions of everything. And this is why we need evolutionary architecture. So as we can see, change is constant. Nothing stays the same for long. And as we're building these solutions, we need to keep up with these changes in user requirements and external policies. And we live in this agile focused industry where change is accepted and even expected to some degree. So what we don't want to do is build these brittle architectures and solutions that can't adapt to this level of change. So if we looked at an extreme version of what can go wrong when you don't build evolutionary architecture, we could look at this case back in 2013 of the US government's healthcare website. This rollout cost 840 million US dollars, and it was built by many different contractors. So this was a very complex and brittle architecture that could not cope with the constantly changing requirements and last minute changes in policy. Now, the outputs of that were that it couldn't scale. Latency on average was 71 seconds. And on the initial day, 4 million unique visitors actually went onto the website, yet only 6 people could actually enroll in health plans that day. This was all because this architecture at a code level and architecturally could not adapt to change. So let's flip it on its head. Let's have a look at a good example. Now, this is an example by the Prime Video Tech team. A lot of noise in the industry happened when this first came out. And this was specifically their video quality analysis system, which was built using step functions and Lambda functions. It was very serverless driven, all orchestrated with step functions. But at scale, it actually costs a lot more than they expected, and it didn't quite scale as they initially planned. So because they'd built this using evolutionary architecture, they could reuse all of the business logic and then change the actual overlying architecture. And they, in fact, moved this to ECS and more of a monolithic architecture. And if we look at this quote, it is conceptually the high-level architecture remained the same. We still have exactly the same components as we had in the initial design. And this allowed us to reuse a lot of code and quickly migrate to this new architecture. And Dr. Werner Vogels, who's the CTO of Amazon Web Services, went on to say, building evolvable software systems is a strategy, not a religion. And revisiting your architectures with an open mindset is a must. And then he went on to say, I always urge builders to consider the evolution of their systems over time and make sure the foundation, meaning evolutionary architecture, is such that you can change and expand them with the minimum number of dependencies. And another great quote is from Neil Ford from ThoughtWorks. He wrote the book on building evolutionary architectures. And he said the goal of evolutionary architecture is to enable a system to evolve gracefully as user requirements and environmental constraints change. Now, evolutionary architecture is not new. It's been around a long time. Everything from hexagonal architecture to more cloud-native approaches that we have today. So hexagonal architecture was first coined by Alistair Cockburn back in 2005. And the main premise here was that the inside part should not leak into the outside part, meaning the core business logic should not leak into the technology and frameworks. And although his original diagrams had 6 sides, this is where the hexagonal architecture came from, you could actually have a UI in a database, which obviously would be one driven adapter and one driving adapter. So in the end, they call this ports and adapters. You could have many, many different ports and many, many different adapters. And it was all about this key abstraction between the domain logic and the technology. And then Jeffrey Palermo in 2008 came up with this concept of onion architectures. And we can see on the right-hand side here, it's made up of concentric rings, a bit like the layers of an onion. And essentially, it's the same thing. The domain services and domain model are all about the business logic. And as we get further to the outside layer, this is where we've got everything from technology, services, and frameworks. And this had a key focus on dependency injection and inversion of control. It also had an unashamedly bias towards object-oriented programming. It was not functional at all. And then last but not least, let's look at Clean Architecture by Robert Martin. And this was discussed in his book, Clean Architecture in 2012. And this combines the principles of hexagonal architecture, onion, and all these other different variants. And we can see on the right-hand side, it's very similar. We've got use cases and entities on the inside, which is your business logic. And we've got controllers or adapters that then interface with technologies and frameworks. And one thing I love is this notion of screaming architectures that he came up with. So it should be extremely obvious when you look at it in an application or microservice, what it actually does. And one of his quotes, again, which I love, is when any of the external parts of the system become obsolete, such as a database or a web framework, you can replace those obsolete elements with minimum of fuss. So if we look at all these different patterns, there are 4 key things that they achieve. So we've got adaptability. So you should be able to change just a part of the architecture or part of the code without changing the whole. And then we've got modularity. So we need to try and keep different parts of the system separate. So business logic away from technology and vice versa. And it should be independent from frameworks. So we should be able to swap out one framework for another very easily without having to change everything. And again, one of the key tenets is testability. How do we make testing easy? So if we now fast forward into 2024, we can start looking at cloud native approaches. Let's first have a look at what most people do when using Lambda functions. So what most people do, and I've seen this in many organizations in many different sectors, is they do actually mix business logic and services. So they go against all of these core tenets. So a Lambda handler has everything and the kitchen sink in it. So you can see here, we've got the handler code, we've got request response mappings, service code, business logic, framework, input validation. It has everything in here. And this is very brittle and very difficult to change. And it doesn't allow us easily to swap out one service for another or move, say, between functions and containers. And it's very difficult to actually test without doing a lot of mocking. And when we do make a change to a service, we then have to change all the mocks, which isn't great. And that's just one Lambda handler. Could you imagine if you've got hundreds of Lambdas? We've then distributed this complexity across all of them. So we're now having to change many, many files if we want to swap one technology out for another. And again, looking at screaming architectures, it isn't obvious what this microservice is actually doing. Very difficult to see. So this would be an example of what I would call a bad Lambda handler. So we can see it's all to do with API gateway. This is how it's been invoked. It's got specific code there for Lambda functions. So we can see it's doing a JSON parse on the body. It's doing some domain specific, so schema validation. It's got business logic, checking that you have at least one domain owner on the object. Again, more domain specific. And then it jumps to an adjacent list pattern in DynamoDB. And then again, service specific, it's doing a put item. It's then sending that using the DynamoDB AWS SDK. Domain specific, again, creating the right domain response. We're doing some metrics, again, service specific. And then we're returning the response, which is, again, very specific to API gateway with the status code and the JSON stringified body. So this is not evolutionary architecture. So it's very brittle. We've mixed the service-specific code with the domain and the infrastructure. Unit testing requires lots of mocking, and it's very difficult to change. It's now very difficult to swap out one framework or service like DynamoDB. We're then having to change many, many files just to swap that out. And again, changing domain logic can be across many, many files. And this is where I came up with two approaches, the lightweight clean code and the full clean code examples. Now, I've used this at various organizations now, and it works well and does actually scale. So if we first look at the lightweight clean code pattern, this allows for evolutionary architecture. We can see we've got primary and secondary adapters here, those blue boxes. So primary is the adapter for the technology coming in. So it's API gateway in this instance. And going out, we've got adapters or secondary adapters for writing to DynamoDB or publishing events to EventBridge. Now in the middle, we've got this notion of a use case. And that use case is the business logic that then talks out through secondary adapters when it wants to persist data or talk to a particular technology. And this approach allows you to start with the lightweight version and go full if you need to, if you've got that complexity. Now, if we looked at the folder structures, what we would see here, again, it's very easy to reason about. We've got an adapters folder. We can see we've got primary adapters for the things that are coming in, so API gateway handlers in this example. We've got secondary adapters, like we said, for talking out to DynamoDB and Amazon EventBridge. And we can see we've got our use cases here, which are pure business logic, don't have any technology whatsoever within them. We want to keep it modular and keep them completely separate. And you can see from the folder structure, each of these would be a different API endpoint. So we've got add song to playlist, create customer account. These would all be separate Lambda functions. Now, say we've got a lot of business logic, lots of rules, maybe calculations. We might want to go to this full clean code version. So we still have the notion of primary and secondary adapters. That doesn't change. But now our use cases deal with entities. And these entities are something like an order or a user, which has an ID. So an order would have an order ID. And it always has to be in a valid state. So it could have its own rules and invariants on it. And then the use case would orchestrate multiple domain entities for its own wider business logic. And now use cases use repositories as an abstraction to talk out to these secondary adapters. That allows us to now change in one place in this repository file, swapping out that secondary adapter very easily. Now, if we look at the folder structure, it's very similar to what we had before. There's just some additional folders. Again, we've got our primary and secondary adapters in the adapters folder. But now we've got domain entities in this domain folder. These are classes for things like user, customer, or order. We also have this DTO folder for things like types and interfaces. And we still have our use cases, pure business logic, but we now have this repositories folder which, as I said, is an abstraction between the use case and the secondary adapters. So let's have a look at an example of actually swapping something out. So in the previous example, the input was API gateway, which had the Lambda handler. But let's say we now want to do this rather than synchronously, we want to do it asynchronously. So we can swap out and do a storage first pattern. So maybe it's API gateway to SQS, and then we invoke this Lambda. So we can very easily, without changing any use cases, any tests, any secondary adapters, we can take out that adapter, plug in a new SQS adapter, and everything else remains the same because we've built it in a modular fashion. Now, say another requirement comes in that we no longer actually want to publish to Amazon EventBridge, we want to publish to SNS. Again, we simply swap out that adapter for an SNS adapter, and everything just works exactly the same. Now, we could also go to containers, for example. So here we can see that our entry point is now an Express app or a Fastify app, and we're now going to run this on ECS. So again, rather than having all of these different adapters for Lambda, we now just have one for ECS. And if we have a look at an example of that, all we would do, again, in our primary adapters, because this is how the API is being invoked, we now create an entry point for a Fastify app, and we call this order service.adapter. So nothing else changes. It still uses the use cases, and those use cases still talk out either through repositories or directly to secondary adapters. So we've essentially created one file and moved from functions to containers. So that's all theory, that's all diagrams. Now let's have a look at some actual code. So we can see here, if it was API gateway, this is what our primary adapter might look like. And this is devoid of any business logic. We can see it simply takes the payload, it validates it with the schema validator, and it then calls this create customer account use case. That's going to do all the interesting work, return this created account, and we simply return this with a status code of 201. Now the use case, we can see the comments at the top here. This allows us to do our screaming architectures, so we can generate documentation using TypeDoc. And you can see here there's no notion of technologies whatsoever. It takes a particular DTO, new customer account DTO, it returns a customer account DTO, and all it's doing is some schema validation, and then using secondary adapters to actually create the account and publish the event. We don't know what the underlying technology is. The use case doesn't care. And then we'll look at the secondary adapters. So this one is specific for DynamoDB. So this create account function takes this DTO object. It then uses a put item input. It saves that into DynamoDB and then just returns it to the use case, the actual DTO. And you can see here we've also got a function for updating an account or actually retrieving an existing account. We could obviously swap this out as an implementation for something like MySQL or DocumentDB, or essentially any framework or technology with minimum of fuss. So let's look at how we would do this with containers as well. So again, we said earlier, we create one entry file, and we're going to use Fastify. We could have used Express or another service. We set up the address, the port, and what we'll see earlier, it was API gateway invoking a Lambda handler for a particular route. Now we're using Fastify, so we've got this post on /orders, but essentially it's the same premise. It's doing some validation of the payload and then calling the exact same use case. Now, obviously what we would have here is a different Fastify endpoint, which calls each of the different use cases. So you might look at this and say, well, Lee, what about dependency injection, inversion of control, IOC containers, everything that we talked about earlier in the presentation? So for me, it's all about simplicity and modularity over complexity and layers. So serverless is known for speed and simplicity, so we really need to focus on this. And we also need this key focus on modularity. So Personally, I don't think we need dependency injection, IOC containers, especially with TypeScript. Now, that might be different with other languages like .NET or Java, but for me, we can simply use the module system and imports along with interfaces. And you do whatever works for your teams. The pattern still remains, regardless of what language you use. And another key tenet is you probably don't need many levels of inheritance, lots of layers of abstraction and object-oriented programming. So keep it simple and functional. There's no need to go overboard. So as a quick summary, evolutionary architecture is not new. We've talked about it. It's been going since 2005. And we have had to adapt these patterns, obviously, for cloud native solutions, especially when we've got serverless as a paradigm. It's completely different. And we should also focus on the simplicity that serverless gives us. So don't overdo the dependency injection, inheritance, and the amount of files. We should be able to make changes very quickly when a change is needed. And one of the outputs that we haven't actually talked about is having this convention and folder structures and pattern. We can actually auto-generate a lot of our code. Now, I can't cover that today, but if you look on my website, serverlessadvocate.com, I do show an example of using a CLI, which can auto-generate a lot of this for us. And that reduces cognitive load on teams and obviously increases the delivery speed. So all of the articles and code can be found at that QR code there or serverlessadvocate.com. If you've got any questions, please reach out on social media. Thank you very much for listening today.